Okay, so boiling point would increase. There's also, there's another factor at work here too. It's not just the clinginess of these ionic compounds, because truly it's based on the concentration, not the type. What if I threw a different kind of solute in here? It's also the point that the surface area, it's it's completely water, right? Well, if I start adding solute, then it's breaking up the water at the surface. And if this is some other covalent compound, let's say, that's taking up surface area, then there's less surface area for these water molecules to break free. So there's a couple different things here. You've got this static interactions, you've got this taking up more surface area action, and I don't care how they ask it or what they ask it. You just need to know that boiling point would increase and that the surface area is, you have less surface area for the water to escape or the static interactions. One answer is going to be correct on the test. And if you see either, then answer that answer, right? Okay. Vapor pressure is measured using the units of atmospheres. It's called ATMs, atmospheres. What would most likely happen to the vapor pressure if 25 grams of salt was added to a closed container with 1 liter of water and a vapor pressure of 0.050 atmospheres? Explain why this happens. It's the flip side of this boiling point coin. If I have this closed container and that the water vapor pressure is at 0.050 atmospheres, it's going to lower it. It's going to lower the vapor pressure. Right? So we're going to lower that vapor pressure. Same explanation. If it's taking up surface area, if you've got these static interactions, it's not allowing the water to vaporize. You're going to have less vapor pressure. Do I need to draw another picture of the same things over and over again? Probably not. A term used that, there we go. A term that is used to describe two liquids that are soluble. So that's miscible. Miscible. What are the two colligative properties that are affected by a solute? All colligative properties are affected by a solute, but they are boiling point elevation, freezing point depression, and vapor pressure lowering. Which colligative property decreases by adding more solute to a solution? Decreases. Well, you have freezing point depression and vapor pressure lowering, both of those. So I don't know. I'm just going to put freezing point depression. I didn't realize we were talking only about 2 from here on out, and vapor pressure lowering. They both decrease according to the amount of solute. Which colligative property increases by adding more solute to a solution? That's boiling point elevation. Wow, we're asking the same questions a lot, aren't we? That's okay. What types of compounds form electrolytes? Okay, so we talked about electrolytes a long time ago. And basically, ionic compounds, we said that ionic compounds use that D word, dissociate, when they go into liquid. So these ionic compounds go into liquid and they form their ions. And what these ions do is make it very easy for electrons to travel through the water. Without these ions, if you have distilled water and all the ions are removed from it, very little electricity can flow through it. So you have to have some kind of ionic, some kind of ions in there for electricity to flow. And that's called an electrolyte. When you drop an ionic compound into a water, that's called an electrolyte. Now, you're used to Gatorade. Gatorade is an electrolyte. It's got salt in it, right? And your body needs those electrolytes. You have electricity that needs to travel all around your body. You have muscles that need to operate. You have synapses that need to fire. You have nerve endings that need to go. All these things are aided by electrolytes. So ionic compounds, solutions. And we just explained why, because they break into they dissociate into their ions. And that's why, that's what forms an electrolyte. That's also why lightning can strike ocean water like 5 miles away and still fry someone over here, because there's a lot of salt in the ocean, and salt is a great electrolyte. Okay, which of the below best explains what happens when salt dissolves in water? Polar solvent molecules surround only the positive sodium ions. That makes no sense whatsoever. The polar solvent molecule surrounds the positive sodium ions and the negative chloride ions. That 100% true, so let's kind of circle him. But you got to read all the answers. Don't come to the first answer that you think is correct and go, yep, that's it. You got to make sure the other ones sound dumb. The solute and solvent molecules form a crystalline structure. That's idiotic. Yeah, that's an obvious wrong answer. The solute and solvent particles do not interact. Well, if you put negatives and positives into water, which is a very polar substance, right? We've got negative charges, we've got positive charges. It is surely going to interact. So I think we can go with B safely now. All right, how many grams of sodium nitrate are in a 5-liter, 3.5 molar sodium nitrate solution? Well, seems like a molarity problem again. Again, molarity is equal to moles over liters. So we got to go to grams. So I know my X is going to be on top. I know that it's going to be in 5 liters. I know that it's going to equal 3.5 molar. That's going to give me my moles. 5 times 3.5 equals. No. 5 times 3.5 equals 17.5. So I have X equals 17.5 moles of sodium nitrate, NaNO3. Do I have that right? Nitrate. I'm not going to take anything for example for, oh, yeah. Okay, so I do have that right. NaNO3. And now I got to take NaNO3 and go from moles to grams, because remember, I wrote units here, and they're not asking me how many moles, they're asking me how many grams. So I need to do a little dimensional analysis with 17.5 moles. Hopefully you can. 17.5 moles, and I'm going to grams, and so that means this is 1 mole of NaNO3, and I need grams of NaNO3. All right, so we got 3 oxygens, 3 times 16, plus 1 nitrogen, plus 1 sodium at 23. All right, 85 more or less grams times 17.5. So I get 1,487.5 grams of NaNO3. Complete units are best, even though I didn't do them right here, so you can scold me later. Okay, scold me later, not scald me. That is page 1 in the books. Page 2. All right. Calculate the molarity. As soon as I see molarity, I know what formula I'm going to need. Calculate the molarity of 200 milliliters of solution containing 100 grams of nitric acid. Well, I don't see grams anywhere on here. I see moles, and I don't see milliliters anywhere on here. I see liters. So the first thing I got to do is convert these milliliters. If I divide 200 by 1,000, I get 0.2 liters. Remember, it is milliliters divided by 1,000 equals liters. And I got to do 100 grams of HNO3, so I have to convert that to moles. So let's do that. 100 grams HNO3, grams HNO3, 1 mole HNO3. All right, 3 times 16 inner plus 14 inner plus 1 inner. That is 63 grams per mole. So 100 divided by 63. I get 1.5873 moles. Divide that by 0.2 liters. I get 7.936, etc., 5 molar. That is my answer, because it says calculate the molarity, so I just did 7.9365 molar. How much concentrated 6 molar HCl is needed to prepare 150 milliliters of 2.5 molar solution? Okay, so this is a serial dilution problem. If you are not in honors chemistry, well, even then, we didn't go over serial dilution. Maybe I will on Monday, but I'm going to show you how this works. It's pretty easy. It's would you, for the love of Pete, just leave the lights on? Okay. So basically the formula is M1V1 equals M2V2. And that is molarity 1 at volume 1 equals molarity 2 at volume 2. And the way this works is I'm trying to make a 2.5 molar solution at 150 milliliters. So 150 milliliters. And here, I don't have to convert to liters. As long as I know that it's milliliters on the other side. This is just kind of like a proportion. And I know that I want it to be 2.5 molar, and I know that the other side is 6 molar and X milliliters. And that's the way that's set up. X milliliters of 6 molar solution to make 150 milliliters of 2.5 molar. And the way I would do this, when I get this milliliter amount, I'm going to take that milliliter amount and I'm going to add enough water to get to 150 milliliters, and that's going to give me a 2.5 molar solution. I'm thinking I'm going to have about, well, a little less than half as much as this, because this is 6 molar. This is a little less than 3 molar. So I'm going to have 75 milliliters or less. So let's see what it turns out to be. So 150 times 2.5, enter, divided by 6, enter, 62.5 milliliters. Hey, I was right. 62, so 62.5 milliliters. That is my answer. And I'm just solving for x, multiplying these two, and then to isolate x, I'm dividing by 6 and dividing my answer over here by 6. So yeah, so that's where we're at right now. 62.5 milliliters, which is less than 75, little less than 75 milliliters, so that makes perfect sense. All right, to what volume should 125 milliliters of 10 molar H2S should be added to produce a 3? Again, M1V1 equals M2V2. Same thing over again. I'm trying to produce a 3 molar solution, right? And I need to know how many milliliters. To what volume? That's not good English. To what volume should 125 milliliters of 10 molar H2S should be added to? That doesn't make any sense whatsoever. But again, doesn't matter. 125 milliliters of 10 molar. Okay, so 125 times 10, enter, divided by 3, enter. So I need 416 milliliters. So now remember, now I have to add to this volume of 125 milliliters, right? And I have to get it up to 416 milliliters. So 416 minus 125 is what I'm actually adding. So 416 minus 125, the original solution. So I need to add 291 milliliters of H2O. Okay. So then, yeah, you're not going to have anything. I don't believe. Maybe you will. I don't know. It's just an extra step. It's an M1V1, M2V2 problem, but you have a finished volume, a final volume. So if I want to make, if I'm starting out with 125 milliliters of 10 molar, and I want to get to 3 molar, I basically have to add 291 milliliters of water so that this gets to be 416 total milliliters. How can you get oxygen gas to dissolve in a fish tank? Okay, well, other than this might kill the fish, you can cool the water down. Because remember, solubility curves for a gas look like this. At low temp, we have a lot of solubility. At high temp, we have very little solubility. So if we want a gas to dissolve in water, we should keep it at a low temp, right? Yep. Okay. What is the correct relationship between solubility of a gas in a liquid and temperature? Well, I just said it. I even drew a little picture here. The correct relationship is as temperature goes up, solubility goes down for a gas. So as temp goes up, solubility goes down. Also called an inverse proportional relationship, right? Well, if this wasn't it'd be inverse proportional. Anyway, doesn't matter. As temp goes up, solubility goes down. What is the correct relationship between solubility of a solid and a liquid and temperature? Well, we've got the solubility curve, and this is a gas, right? This is the only gas in here, NH3. All this other stuff is solids, and whether it's going up a lot, straight up, or whether it's like NaCl and it's just going up a little, what you need to know that as temp goes up, as temp rises, solubility rises or increases. As temp increases, solubility increases, right? So as the temp gets higher, the solubility for everything that is a solid goes up, and the solubility for a gas goes down. Okay? Okay. Which substance is least soluble in 100 grams of water at 90 degrees? Well, that's simple. You go to 90 degrees, you go up till you find your first thing that you run across, and that is NH3. Not a shocker. It is a gas. And that's how you figure that out. You just go to the temp, go up until you hit a line. That is your least soluble. Only 10 grams will go in at 90 degrees, whereas 40 grams of NaCl, 40 grams of KCl. Wait a minute, where am I at? 90 degrees. 50 grams of KClO3, 52 grams of KCl, 70 grams of NH4Cl. You see what I'm getting at? Okay. If a saturated solution of potassium nitrate in 100 grams of water, everything is in 100 grams of water. You need to realize that this whole chart is in 100 grams of water. If a saturated solution of potassium nitrate in 100 grams of water is cooled from 70 to 40, how much precipitate will form? Well, we did this lab, right? We did a KNO3 lab. We took KNO3 and we heated it up until everything dissolved, and then we cooled it down. And as we cooled it down, it started to crystallize. So what you need to do is look at how much a saturated solution at 70 degrees will hold, how much a saturated solution at 40 degrees would hold, and subtract the one from the other. So at 70 degrees, KNO3. That's 130 grams. And at 40 degrees, that is, I'm going to call it 62 grams. 130 minus 62. 68 grams will precipitate out. 68 grams KNO3. That's my answer. And it makes sense. If I heat this up to 70 degrees and I saturate it, I'm going to get 130 grams in there. Then if I cool it off to 40 degrees, and we're going to ignore supersaturation at this point, we're going to say that that never happens. Which any question like this, you have to ignore the idea of supersaturation. But if I cool it down to 40 degrees, only 62 grams can actually stay in solution, dissolve. So the rest of this has to fall out as a precipitate. So 130 minus 62, 68 grams. How many grams of ammonium chloride can be dissolved in 100 grams of water at 50 degrees? This is the easiest kind of question. It's in 100 grams of water. All you're doing is going to 50 degrees, going up to the NH4Cl line, 50 degrees, NH4Cl, and then going over to see how many grams. That is 50 grams, yo. NH4Cl. Okay, at what temperature will 150 grams of potassium nitrate KNO3 dissolve in 200 grams of water? Well, this seems like a, yeah, this is an interesting one. Wow, this is an interesting way to answer a question, isn't it? So basically, I'm going to figure out when half of this, 75, can go into 100 grams of water. At what temperature 75 will go into 100 grams of water, and that is the temperature that 150 will go into 200 grams of water. So I'm just going to do kind of a proportionality, but I figured this one out in my head that half of 200 grams is 100, which is what we need to look right directly at the chart. And half of 150 grams is 75. So let's just go to KNO3, go to 75 grams, which I'm going to say is right here. And then go down, and I'm going to say that's 48 degrees Celsius. Yeah, that's really all the extent that I'm going to spend on that question. So let's just get on with it, shall we? Now, solving proportionalities, we'd love for you to be able to do, this proportionality is almost trivial at 200 grams of water. If it's any multiple of 100 grams, you know that you can just multiply whatever comes straight off the chart in 100 grams of water and double it. So at 50 degrees KClO3, I don't even have to solve a proportionality. KClO3 at 50 degrees is 20 grams. So if 20 grams will go into 100 grams of water, then 40 grams will go into 200 grams of water at that 50 degree temperature. So my answer is 40 grams. I mean, you could set up a proportionality for this, but really, this is pretty easy. This is like that 2 out of 10 that I was talking about in class. All right, at 50 degrees, if a solution contains 80 grams of KCl, how many grams of water is needed? Okay, so we have 80 grams of water. 80 grams of KCl. Oh my God, I got 24 minutes in this video. Oh, hang on.